This conference will now be recorded.
Hello everyone. Today's topics will be comparison between 3s, 3p, 3d, shapes of orbitals, radial and angular nodes in p and d orbital, and there will be some related problems. In last class, we have already seen what is radial distribution function, how it varies with distance r. Now some more examples of this radial distribution function we will see. Here, as you can see, 3s orbital is chosen. So 3 pictures are there. All are related to 3s. But what is the difference? Try to understand. In x-axis, it is r for all these 3 graphs. But in the y-axis, there is some difference. So here, radial part of the wave function, that is capital R, which is function of distance r. So that is why in bracket it is written small r. Then if you take the square of it, which basically we call radial visual probability density, fine. And when r square is multiplied by the volume element, which is 4 pi r square, sorry, it's 4 pi r square, then it is radial probability. But if you divide it by the volume, that is 4 pi r square, and dr also element, there is another component, but for simplicity it is simply 4 pi r square r. So this is radial probability, but if you divide it by the volume, then it will get radial probability density. Now why these three it is important for you to know, because in question different types of graphs may be given. Okay, so that is why if we have prior idea about that, it will be helpful for us. So when it is simply RR, how it is changing with distance r, you can see there are some points where it is directly touching this x-axis, and when there is no square, that is simply r, then even it can have negative value. See, it is passing through this and it is going towards the negative because it is negative, this is positive. So that is why when you have not taken the square of it, when it is touching the axis, that is where the nodes will be there. These two are basically nodes because at these 2 points it is touching r. Okay, so that is why we are getting total 2 nodes. Now for different types of orbital, how to understand that how many nodes will be there, that we will discuss separately. Fine. Right now just see how RR it is changing with the distance from the nucleus. Fine. So 2 nodes are there. Then when it is squared, now there will be no negative, because now you have taken the square, so negative sign cannot arise. So that is why here also we are getting 2 nodes, because it is touching this x-axis at these 2 points, but there is no negative. All these humps that you can see, these are the 2 humps, all are towards the positive side. And when it is 4 pi r square, then there are total 3 humps, because now it is starting from 0. So these are the difference between these 3, but common point is that in all cases you are getting 2 nodes. That is fine. Okay. Now we will also see it for 3p, because we are just comparing 3s, 3p, 3d. So in case of 3p, now here also we are getting this node, only one node is there and it is going towards negative side. But when you have taken r square, there is no negative, and 4 pi r square, capital R square, that is also basically it looks just same as the second one. And for 3d, there is actually no node. For 3p, there is actually one node. This is one node, here also one node. So whatever graph you take, whether it is RR or R square or 4 pi R square, in all cases you will see it is basically same node will be there, because after all it is 3p. Fine. So node, how many nodes are there, that will always be same, but nature of the graph may change or it may not be, because when you consider the 3D, now as there is no node, whether you take R or R square or whatever, as there is no node, so in all these cases it looks same. So see, these three are actually same. So in this way we can compare 3s, 3p and 3D, and how the nodes are changing, how the graphs are changing. It depends on in y-axis what you have chosen. Now, if we compare these 3s, 3p, 3d, their penetration power, fine. So penetration power, if we want to check, we know that 3s is more penetrating compared to 3p, and 3p is more penetrating compared to 3d. Now, penetrating means it is move, that is towards nucleus. There will be some approach. So that is why it is a penetration power, which is maximum for 3s. Now, how we can prove it from this diagram? So see here, single picture is taken where 3s, 3p, 3d you can see simultaneously. So we have taken it together so that we can compare. So for 3d there is no node, and this is the maximum. For 3p you have to choose the second hump because height is high. So this is the R max, maximum R value for this maxima. And for 3s there are 3 humps, but we have to choose the last one because this peak height is high. Now you can see R max for 3s it is here. For 3p it is shifting towards left hand side compared to 3s, and for 3d again it is shifting towards left hand side. That means R max for 3d is minimum, then it is 3p, and maximum value is for 3s. So it proves as R value is increasing from D to P to S, it is basically the proof that penetration power will be maximum for S orbital, then P, then D. Now it is not just for 3s, 3p, 3d, it is actually true for any SPD. And here we have taken 3s, 3p, 3d to understand this concept, but it is true for any SPD. So when the value of n is same, then only you can compare it. So it may be that you have taken 4s, 4p, 4d, that is also okay, but same value of n must be there. So for same value of n, the distance of maximum probability of different orbitals, that is actually inversely dependent upon the value of L. Why it is so? Because for 3s the value of L is 0. For 3p, not just 3p, for p orbital it is basically 1, and for d it is basically 2. That means when L value is increasing from 0 to 1 to 2, then the maximum probability of these different orbitals, okay, that is inversely related, because now this R max value, that is actually decreasing when L is high. So L is high, R max is decreasing. So that is written in this table, and it proves that penetration power of an orbital, it is maximum for S, and this is basically a measure of its closeness to the nucleus. Okay, so this is the definition of penetration power. Now, because of this additional maxima in 3s curve, an electron in 3s, it spends some of its time near the nucleus. Fine, because of this additional maxima in 3s curve. And that is the reason why it is more penetrating than 3p, and 3p is more penetrating than 3d. Okay, so this is the explanation why this penetration power is decreasing from S to P to D. Fine. Now, related to this type of radial distribution uh, or radial probability distribution, all these uh, graphs, if we consider related problems, we'll discuss now. Here the problem is saying which of the following is the correct plot for the probability density chi-square. Now the previous plots that you have seen, they are not chi-square but capital R is given, but actually these two are analog. Basically capital R, it is the radial part of the wave function. We have seen in the last class that there is radial part, there is angular part. So this graph, it is basically for radial part, but sometimes in question you may find that instead of capital R, chi-square is given, but nature of the graph will be same whether you have taken chi-square or R, capital R. Basically this chi, by this chi here, it is trying to focus on capital R, fine, radial part. So 4 graphs are given. We have to choose which of the following is the correct plot for the probability density of chi-square function of small r. That means here radial part is considered, fine, not the angular part, as a function of distance r, which is in the x-axis of the electron from the nucleus. And it is for which orbital? That is important. It is for 2s orbital. Okay. Now for 2s orbital or any other orbital, how to calculate node, that we will just discuss after some time. Right now I'm just giving you the formula, that is to calculate how many radial nodes are there. We use this formula, that is n minus L minus 1, where n is principal quantum number, L is azimuthal quantum number. Okay, so for 2s you have to put 2, then for L it is 0 and 1, that means it is 1, so only one radial node will be there. Now this much information is enough to choose the correct option, because if you look at the first one, basically chi-square graphs, it is never having this type of nature. Whenever there is chi-square, you will see it will start from 0, but here it is not starting from 0. But you don't have to focus on that, as you have obtained from this formula that radial node is only 1. So look at the graphs carefully. In which graph there is only one point where it is touching x-axis? It is only option B and C. In C also, this is the point where it is touching x, and in case of option B also, it is the point where it is touching x-axis. Fine. But if you consider the last picture, it is basically touching at 2 points. So this cannot be correct. Now you are stuck between C and B. So how to choose it? It is very easy, because we have already seen, remember the first picture of today's class, chi-square, as there is a square, it cannot be negative, but here it is negative, right? So this cannot be correct. Considering all these facts, you have to choose option B as the correct option. Now for more information, because you may get different types of problems, so it is better the more you can familiarize yourself with more this type of plots. It is better for you, so that you can solve problem easily. So see, here I have presented some more graphs, because so that you can solve different types of question. This is for 2s, fine, but it may be for 1s or any other orbital. Here we have 1s, 2s and 2p. And all these graphs are basically only capital R. So that is why negative value is possible. So for 1s, this n minus L minus 1, this is basically 1 minus 0 minus 1. That means it is 0. So that is why you will not find any node in 1s. But for 2s, we have already seen there is a node. But this picture is matching with option C, isn't it? Because there can be negative value. But option C, this picture you can find similarity, but this is not the correct option, obviously, in case of this question. And for 2p, this n minus L minus 1, this is actually 2 minus 1, because for p orbital azimuthal quantum number is 1. Again you are getting 0. That means no node will be there. No node. So see, you are getting no node. So this picture is only for capital R, but the next picture again it is for same orbitals, 1s, 2s, 2p. But see, now it is square. Okay, so this is square for all these three, and this picture is actually present in option B, and that is the correct one. And just based on this information that only one node should be there, we have chosen option B, because in option A and D there is here we have 0 node, here we have 1 node, here also we have 1 node, but here we have 2 nodes. So you can easily cancel option A and option D, but between B and C we have chosen B, because negative sign should not be there, as it is chi-square. It is already mentioned in the question, it is chi-square versus R graph. Okay, now when it is changing from R to R square, don't think that node will be changed, node will remain same. So that is the reason here also you can see 0 node, 1 node, again 0 node. And if you take 4 pi R square, then capital R square, then the graph, its nature will be completely different. See, now it is starting from 0, only one hump is there, but again, as I have said, node number it will never change, it will be again 0 node. For 2s also only 1 node, and for 2p there is 0. Okay, so in this way you can solve graph related question like this easily. One more problem. The plots for radial distribution function for various orbitals of hydrogen atom against R. Now all these 4 plots, you can see this 4 pi R square, that is multiplied with R square. Okay, sometimes it may be R square, sometimes it may be 4 pi R square multiplied with R square. Okay, now here we have to find the plots for rate resistor function for various orbitals of hydrogen atom are given below. That means all these are for different orbitals of hydrogen, but you have to find the correct plot for 3s orbital only. Now again, if you apply this formula, n value is 3, L is 0 for s orbital. So how many nodes you are getting? You are getting 2 nodes. So first graph there is actually 0 node. Second graph there is only 1 node. Third graph there is again 0 node. And the fourth graph there is 2 nodes. So now you can decide which one will be correct. So here number of radial node, please see it is radial node because nodes can be different type. It can be angular nodes also. Details we will obviously discuss. But if it is radial node only, then that is when this type of pictures will be given and you have to check how many nodes are there. Obviously you have to use this formula because these graphs are only related to the radial part of the wave function. It has nothing to do with angular. Okay, so for this type of graph, when you will choose the actual graph, you have to choose the formula for radial node, n minus L minus 1 for 3s orbital, principal quantum number 3, azimuthal is 0 for NUS orbital. So that is why you are getting the value of radial node 2. So based on this, you can choose that last option. That will be the correct option because in all other cases, number of nodes are either 0 or 1. Only in last one, these 2 nodes. Fine. Now, before going to the discussion of how to understand radial node and angular node, first we will see shapes of orbitals because when nodes will be discussed, we will directly use the different pictures of p orbital, d orbital, s orbital. So if you do not have prior knowledge of about the shapes of the orbitals, it will be difficult for you to understand the node. So that is why first we will see how to understand the shape of different orbitals. Fine. Now, until now, we have discussed only about the radial part of the wave function, but we know there is another part which is angular part, and this angular part or angular component of the wave function psi is actually responsible for the basic shape of the orbital. Detailed calculation, obviously, it involves higher mathematics, and that is not required for your syllabus. Just you remember this fact that the angular component of the wave function psi, that is actually responsible for this type of shape of different orbitals. S, P, D, F, all are having different types of shapes because of this different angular component of the wave function. Fine. So you can call it as the boundary surface diagram, and it is the surface in the space where probability density is constant for a given orbital. Fine. And these shapes encloses the volume or region where probability of finding the electron is very high. Okay, and it is constant also. Now exactly how to figure it out, for that you can consider this. So see what is written here. Imagine you are standing on the nucleus. Just imagine it. It will help you to understand how we get this idea of shape, because we know that you cannot find from Heisenberg's entry principle the exact velocity, exact position of the electron. That we cannot determine. Fine. What we can talk about the electron, it is only the probability. So when, if you are imagining yourself, you are standing on the nucleus and look around yourself, then the electrons will look as if they are fog around you. Now the square of angular distribution function, that is the angular component of the wave function, its square, that will basically denote how thick this fog of electron is when you look in different directions. So suppose you are looking at a particular direction, you are seeing that the fog is very thin, and you are looking at another direction where the fog is very thick. So where it is maximum thick, That part is actually will give you the idea of shape. Now for s orbital it is very simple, because s orbital it is fully spherical. Though the pictures that you see as it is on the screen, that is on the page of book or screen of the computer, it seems as if it is it's circle, but actually it is not circle, it is three-dimensional, it is sphere. So all s orbitals are spherical in shape. That means what? For s orbital, when you are standing, just imagine you are standing on the nucleus and you look surrounding you in all the areas, because as it is spherical in shape, the fog will be thick. So that is why it is spherical. It is not that at any particular direction the fog is thick. Wherever you are looking, you will always see it is a thick fog of electrons. So that is why it is having a spherical shape. So the probability of finding the electron at a given distance, it is equal in all directions. That is why it is spherical in shape. So when you are moving, whether you choose 1s, 2s, 3s, 4s, whatever, it is always spherical. Okay, it has nothing to do with the principal quantum number 1, 2, 3. No, you just have to know whether it is s or not. Now it is 2s, 3s, whatever, it is always spherical. Okay, only difference is that when you move from 1s to 2s, or you are moving from 2s to 3s, the size of the orbital will increase. That's it. And the distance of finding the electron from the nucleus, that distance will also increase. Suppose if it is 1s, this is the nucleus and electron is here. For 2s, now electron is far from it. For 3s, it is again further. So in this way, the distance of electron just will increase. The size of this spherical shape will increase, but it is always spherical. The size of S4 increases with increase in n. So this is the order, and the electron is located farther away from the nucleus as this principal quantum number increases. Okay. Next, we'll see what about the p orbital. Now, for p orbital, again imagine you are in nucleus, you are looking surrounding it. Now, it is not that the probability of finding electron is same in all the directions. There will be a particular direction where you will find thick fog. In other direction, it is not thick. Now, considering this, the shape of this p orbital, it is now dumbbell shape. So there are two lobes, whether it is px, py, or pz. Now why we have different names? It is because in which axis it is present, because we are discussing it in three-dimensional region, and in three-dimensional three axis you have to consider x, y, z. So if these two lobes are on x-axis, it is px, y-axis py, and z-axis pz. So whatever is px, py, pz, it is always having two sections. That means two lobes are there that are on either side of this, on either plane. That is, if you are considering, suppose here it is px, that means this is x-axis. So when px you are considering, basically it is perpendicular to this zy plane. It is perpendicular to yz plane. Similarly, if you consider py, now it is perpendicular to xz plane. And when you are considering pz, now it is perpendicular to xy plane. Okay, so each p orbital consists of two sections called lobes that are on either side of the plane that pass through the nucleus. So nucleus will be here. Okay, the probability density function is 0 on the plane where the two lobes are touching each other. So two lobes are touching each other. Just consider the last one. This is the plane where they are touching each other, right? Okay, let me draw it like this. This plane is, okay, I'm using different color. Okay, so this is the plane, and one lobe will be above the plane, another lobe will be below this plane. So probability density function is 0 at this plane, okay, where the two lobes are touching each other. The size, shape and energy of these three orbitals are basically same. So they are degenerate. Degenerate means similar energy. Only difference is their orientation is different. Px is along x, py along y, pz along z. Now one more information, just keep it in mind. We know that shape, idea about the shape that we get from azimuthal quantum number L, right? And in case of P, it is 1. Now when it is 1, the possible ML values are -1, 0 and +1. So that is why now you have three different orientation, because ML values, what it explains? It explains that what will be the direction. Shapes are same, whether it is Px, Py, Pz, but direction is different. Now don't try to correlate that -1 is always Px or 0 is always Py or Pz is always +1. So there is no such simple relation between the ML values -1, 0, +1 and the XYZ direction. Sometimes it may be that -1, mostly we say that -1 first, then 0 and then +1. And by convention we usually say X axis first, then we say Y axis, then we say Z. But there is no such simple relation. Keep that in mind. Okay. Next orbital is d orbital. Now for d orbital, azimuthal quantum number is 2. And when azimuthal quantum number is 2, possible ML values are -2, -1, 0, +1, +2. So 5 possibilities are there. So 5 directions, 5 orientations will be there. So all these orientations, you can see the names d, y, x, z, y, z, x, y, x square, y square and dz square. Now we will see this. Fine. Now if you look carefully, these four basically, you can find some similarity. That is the 4 pictures at the 4 corners. And what is the similarity? The similarity is that all are having 4 orbitals, right? But if you look carefully, just forget about sometime what is dz square, because it looks completely different. Just focus on these 4 pictures at the 4 corners. You can find some difference. That is, on one side, suppose you have yz, xy and xz. Another side you have dx square y square. Now why I have written it separately? There is a reason for that. Because when it is dx square y square, see, the lobes are directly on the x axis and y axis, as if it is going through this axis. Okay, it is true that it is on the xy plane, because in the subscript you have x and y, so obviously it has to be in xy plane. That is fine. This is the xy plane, but the lobes are moving through the axis x and y. But if you consider these three, here also the lobes are present in the plane which is mentioned in the subscript. That is, if I am saying it is yz, obviously it is present in yz plane. So this is the yz plane, which is plane of the screen of the computer. Okay, and similarly when it is dxy, now it is on xy plane. So that idea you can get depending on which what is mentioned in the subscript. But what I'm trying to say here, if you look at the lobes and if you compare with the picture of dx square y square, now the lobes are in between the axis. It is not directly on the axis, it is in between. So for all these 3 orbitals, the lobes are in between. But when dx square y square, it is directly going through the axis. That is the important difference. Otherwise, in all these 4, you can find 4 orbitals. So their shapes are actually similar. So that is, it is written, the shapes of the first 4 d orbitals are similar to each other, but the 5th one, it looks completely different, as if it is a p orbital. This part you can find some similar to p orbital, but there is a donut shape also in the center, which makes it different from p orbital. It's not like p orbital, but it is also not like the other 4 d orbitals. But remember, all these 5 3D orbitals are equivalent in energy. Not just 3D, it may be 4D or 5D. Only difference is the size will increase, but basic shape will always remain same. It is also true for p orbital, whether you take 3p, 4p, 2p, whatever, but it will always be having same shape. Only the size will be different depending on the principal quantum number. And here, if you are thinking that why it is mentioned 3D, because that is the first d orbital possible. What I'm trying to say, you cannot have 1D or 2D. 1D, 2D not possible. 1 is possible, 2 is possible. Similarly, 1p is not possible, only 2p is possible. So why these two are not possible? Now the reason is, suppose if you consider 2D, here principal quantum number is 2 and d, L value is 2. But when n is 2, n cannot start from 2. It has to be 2 minus 1, the first one. So that is why 2D cannot exist. The first d orbital, it is always 3D. Because for 3D, n value is 3 and L value is 2, lesser than n, which is possible. So this is the reason the first d orbital is 3D. Then 4D, 5D is fine, but 2D not possible. Now we will see radial and angular nodes. You have already seen the radial nodes, and you also know which formula we use to understand how many radial nodes will be there. So nodes are basically the region for probability density function chi square, or you can say probability of finding the electron, it is 0, and that is called nodal surface or simply nodes. Now nodes may be two types. When you have seen all those plots of radial probability density chi square or 4 pi r square chi square, then you have seen that when it is touching the x-axis, that is the r distance from the nucleus, it is present in x, it is touching the x-axis, then it is actually denoting the radial node. So two types of nodes are there. One is radial node or nodal region, which you have already seen in all those graphs. There is another type of node which is known as angular node or nodal plane. There are different ways by which you can understand how many radial nodes are there, how many angular nodes are there. And if you simply add these two, you can get total number of nodes. So spherical surfaces around the nucleus where probability of finding an electron is 0, that is called radial node or nodal region. And the formula, you can see, we have already used this formula. And as you can see here, 1s, 2s, 3s, these 3 orbitals are given. For the first one, 1s, it is actually 0 node. So these nodes that you are seeing, this is basically, we are talking about radial node. And for 2s, there is only one node. For 3s, there is how many nodes? 2. So how we will get it? You will get it by using this formula. C for 1s, it is 1 minus 0 minus 1, because L values are always 0 for s. And n is increasing from 1 to 2 to 3. So that is why we are getting 0, 1 and 2, which you can see in the picture. Though it is 2-dimensional, but you have to imagine it as if it is 3-dimensional. Now, how to find angular nodes? Angular nodes, basically it has nothing to do with principal quantum number. It is simply the azimuthal quantum number. So that is the reason when it is s orbital, angular nodes are always 0, because for s orbital L is 0. For p orbital, angular nodes L value is 1, so it is always 1. Whether it is 2p, 3p, 4p, doesn't matter, because principal quantum number doesn't matter. It matters for radial node, but not for angular node. An angular node is basically the plane or planar region. See the difference? Spherical surface around the nucleus, where probability of finding electron is 0, that is radial node. But this is actually plane or planar region around the nucleus, where probability of finding the electron is 0. And that is angular node, which is simply the value of azimuthal quantum number. Now to get the total number, you have to add these two, n minus l minus 1 plus l. So l and minus l plus l will be cancelled. So the formula will reduce to n minus 1. Total number of nodes, radial node plus angular node. So this is the formula. How you are getting it? Simply by adding radial node and these two will be cancelled. You are left with n minus 1. We'll see related problems, but before that, let's have a look how you are getting angular node 1 for p orbital. Here we have taken 2px, 2py, 2pz, but you can also take 3p or 4p. But it will always give you angular node equal to 1 because it is related to azimuthal quantum number only. Okay, so when we are talking about angular node, the pictures will be like this. And here you can see if you consider px, that means it is present on x-axis. Now these two lobes, different colors are used. These two lobes, when they are touching each other, that plane there is the probability of finding the electron is 0. And nodal plane is zy plane. So when you are considering px orbital, nodal plane will remain in zy plane. When you are considering py, nodal plane will remain in xz plane. So this is x-axis, this is y, so this is xz plane. When it is pz, now it will be in xy plane. Okay. And for d, azimuthal quantum number is 2. So that is why two nodal planes, angular node must be present. So when it is dxy, that means the four lobes that will be present on xy plane. Now when it is in xy plane, what are the other planes present? So this plane is zy, right? And this one is xz. Okay. So yz and xz, these two planes will be the angular node where probability of finding the electrons. So when it is dxy orbital, the alternative other two planes, that will be the angular node. When it is dxz, the other two planes means zy and xy, these two planes will be the angular node. So in this way, you can see in all cases, there will be two nodes, and the dxz square here, the plane, it looks different. There is a conical type of shape, but remember here also we have two nodes. This is number 1, this is number 2. It is obviously different, having different shape. There is a p orbital and a donut shape together, so it is completely different, and it is not exactly plane, but there is a conical type of shape, and that is considered two angular nodes are there also. So for any d, 3d, 4d, 5d, azimuthal quantum number will give you the how many angular nodes are present. The problem is saying that the number of radial nodes and total number of nodes in 4p orbital. So the first values are radial node, the second values are total number of nodes. So it is 4p. Now for 4, n value is 4, l value is 1 because it is p orbital. Use the formula. Radial node formula we know. This is radial node 2. That means these two you can cancel because 3 and 4 there. And as this is actually angular node, if you add these two, then you will get 3. Or you can simply use the formula n minus 1. It doesn't matter. Same thing. So the answer should be 2 and 3. That is option A. The first value is radial node. Second one is total number of nodes. Second question. Certain orbital has no angular nodes and 2 radial node. From this information, you have to find which orbital it is, because it is mentioned certain orbital. We do not know which ones. But angular nodes 0. That means L is 0. Now L0 means what? It has to be S, right? So these two cannot be correct. How many radial nodes are there? N minus L minus 1, 2. But you already know this is 0. So n value will be 3. So angular node L equal to 0, radial nodes, this information is given. Just put the value of L, and from this equation you will find n is 3. So the orbital must be 3s, because for 3 means n is 3 and s means L is 0. This one correct. Okay, so we have some more time, so we can discuss the next topics, that is energy of orbital in hydrogen atom and also energy of orbital for multi-electron atoms, because hydrogen atom is single electron. After discussing it, we will also see it for multi-electron system. The energy required to remove an electron present in an orbital to infinity. So when you are moving the electron present inside the atom to infinity, obviously you have to provide some energy. But the opposite process, suppose you are bringing the electron from infinity to orbital, then there will be some release of energy. So whether you put energy, the energy required to remove an electron present in an orbital to infinity, or the reverse, that is actually known as energy of orbital. That is, the numerical value will remain same. Depends, when you are moving it from the orbital to infinity, you have to provide energy, so it should be plus sign. But when you are doing the opposite process from infinity, now you are bringing it to orbital, now energy will be released, that means negative sign. But whatever it is, the numerical value, the mode value is same. Now when it is hydrogen like system, there is single electron. The energy of the electron, it is solely determined by the principal quantum number, because there is one electron, so it is obviously present in 1s. No question of azimuthal quantum number. For s orbital, it is 0. So it is now only n orbital which is responsible for the energy of this electron, because we are discussing it for hydrogen atom system, fine, or hydrogen like system. Now the energy of the orbital in hydrogen atom, it will increase in this way. Minimum energy it will be for 1s. Now when you are moving from 1s to 2, there is principal quantum number is increased. Now for 2s and 2p, in both cases principal quantum number is same 2. So these two must have same energy. Okay. Now you are changing the n value from 2 to 3. Now 3 possibilities are there, 3s, 3p, 3d. So principal quantum number same, azimuthal quantum number is changing from s to p to d. But as it is mentioned in the second point, the energy is dependent only on n for this type of system. So that is why these three must be same, and so on. Now if you look at the picture, you can compare with this. 1s is having minimum, then 2s, 2p in the same value of energy, these three same value, these four same. But it is increasing as you are moving from 1 value to 2 to 3 to 4. But within same principal quantum number, it is same. Now it is true that the shape of 2s and the shape of 2p, obviously they are different, that you already know. But the electron has the same energy, whether it is in 2s or it is in 2p. And when orbitals have same energy, we call these orbitals as degenerate orbitals. Remember, the term degenerate means having same energy. Now this is all about hydrogen-like system. But suppose if it is more than one electron, fine. Now the scenario is completely different. We will see that next. Energy of orbital in multi-electron atoms. So when it is multi-electron atom, it is not that you have only one electron. What will happen? Some more things now you can see. We know that when it is single electron, there is attraction with the between nucleus and the electron. So it is electrostatic attractive force, because it is force between two opposite charge, between the electron and nucleus, positive and negative. But when it is more than one electron, so minimum 2 electrons are there. It may be more than that, but minimum 2 electrons when there will be repulsion between these two negative charge. So now electrostatic attraction, that is already present, but now you have a different types of force, which is repulsive force among the electrons. So that is the reason now what happens, the energy of the orbital for multi-electron, it depends on angular momentum quantum number also. So it is not that in the previous system you have seen it is dependent only on n, but now it is also dependent on L, both, because of this new type of force. Okay. So for a given principal quantum number, all these will be having different energy. As we will move from S to P to D, you will see, though it is same principal quantum number, but energy will increase. Within a given principal quantum number, the energy of orbital increase in this order. So as L value is increasing, the energy is also increasing, though principal quantum number is same. Okay. So this type of picture we have already seen in the previous case, but now you can see some difference. Now 2s and 2p, they are not in the same level. 2p is slightly higher than 2s. Similarly 3s, 3p, both are having same principal quantum number, but their L values are different. Here L value 1, here L value 0. So that is why 3p is greater than 3s. Then 4s and 4p, and see 3d is somewhere between 4p and 4s, in between these two. Okay. So in this way it will increase, but how to know which orbital will come, that is after 2s, which one will come? It is fine, it is 2p, but see, as in between 4s and 4p, 3d is there. So how to know which in which order we will move? So for that you have to simply follow this formula. The energy of the orbital, it is determined by sum of n value and azimuthal quantum number. Higher is the n plus L value, higher will be the energy. Okay, so that is why for 1 is n plus L value is basically 1. For 2s, n plus L value is 2 plus 0, that means 2. Here it is 3. For 3s, it is 3 plus 0, that means 3. For 3p, it is 4. For 4s, it is 4. For 3d, it is 3 plus 2, that means 5. For 4p, 4 plus 1, that means 5. Now you can see there is a tie between these two. Now how to choose which one will have higher energy when n plus L value is also same? So for that you have to remember, if two orbitals having same value of n plus L's, you have to choose that orbital as lower energy which is having low value of n. So that is why between 4p and 3d, though both are having same n plus L value, but 3d is below 4p because n value is lesser in case of 3d. Okay, remember this. And another information, the energies of same orbital decreases with an increase in atomic number. So orbital is same. Suppose you have taken only 2s. You are changing what? You are changing the element. So you are moving from low atomic number to high atomic number. Here atomic number 1. Then you have taken lithium, hydrogen, helium, lithium. Sorry, hydrogen, helium is not present here. After hydrogen, we have taken lithium. Then we have taken sodium and potassium. So it is not gradual, but try to understand one thing, as you are changing the atomic number to low value to high, because lithium is having higher atomic number than hydrogen. Fine. Then it is 3. Then sodium, atomic number 11. Here it is 19. So in this way it is increasing. But you have taken the same orbital. You have chosen 2s orbital for hydrogen, 2s for lithium, 2s for sodium, 2s for potassium. Now the energy, how it is changing? The energy of the same orbital decreases when there is increase in the value of atomic number. So that is why the order is like this. Okay. So as we have still time, one more topic also we can discuss, effective nuclear charge. Attractive interaction of an electron increases with increase of positive charge. Suppose we have taken the simplest one, which is hydrogen. So in hydrogen there is only one electron. So there is only single positive charge, that is Z value is 1. But suppose now you have 2 electron. Now here also the value, that is atomic number, it is changing from 1 to 2. Similarly it will be Z2, Z is 3. So as you are moving from atomic number 1 to 2 to 3, electron number is increasing, the proton number in the nucleus, which we call atomic number, that is also increasing. Now with increase in the Z value, the attractive interaction for a particular electron, that will also increase, because positive charge increasing in the nucleus means this attraction will also increase. Now because of presence of electrons in the inner shell, the electron that are present in the outer shell, suppose here I have drawn only one orbital, but if there is another orbital and there is electron present in this outer orbit. So for the red electron, this is outer electron, and these two, they are inner electron. So because of this presence of this inner electron, that is the electron present in inner shells, the electron that is present outside, outer shell, it cannot experience the full positive charge of the nucleus. So as if these two inner electrons, it is playing some screening type of effect on the outer electron. So this outer electron, it should feel the total positive charge that is present in the nucleus. But because of this in-between electron present, that is the inner electrons are present between the nucleus and the outer electron. Because of presence of these electrons, now there will be a screening type of effect, and the outer electron cannot experience the that is actual positive charge that is present. So it will experience something lesser than that, because there is some screening of inner electrons present. This results in decrease in the nuclear force of attraction of an electron because of this partial screening of positive charge by the inner shell electrons. And this is known as shielding, sometimes called screening, of the outer shell electrons from the nucleus, and it is because of these inner shell electrons. Now, as a result, what will happen? It cannot experience the full nuclear charge that ideally it should have experienced, right? But it is experiencing something lesser than that, and that is why we are using a new term which is known as effective nuclear charge. It is not actual nuclear charge; it is effective. That is the resultant nuclear charge. Okay. Here is the shielding. Higher will be this that is effective nuclear charge, that will decrease, because when shielding is very high, it will experience less amount of attraction from nucleus. So this is known as effective nuclear charge, and this is denoted by Z effective. If you simply write Z, it is the actual atomic number, but in the subscript we have written EFF, that means effective nuclear charge. This effective nuclear charge depends on the shape of the orbitals, and it decreases with increase in azimuthal quantum number. So that is the reason the order of effective nuclear charge felt by an electron in an orbital. So suppose the electron is present in P, on another system it is present in S. So when it is present in S, it will feel more effective nuclear charge, because effective nuclear charge, it will the order of effective nuclear charge, if it is so, that means it is decreasing with increase in azimuthal quantum number. So inverse relationship, decrease with increase in azimuthal quantum number. Fine. Greater this effective nuclear charge or Z effective, greater is stability of the orbital, and it has to be, because it is now highly attracted towards nucleus. So it will be very stable condition. Hence, within a given energy level means when n is fixed, that is principal quantum number, if it is fixed under that condition, the energy of the orbital should follow this, because for S, Z effective is maximum, and Z effective maximum means what? It is very stable, and stability high means what? It is having less energy, and when stability is less, energy is high. So if this is the effective, that is stability order, that is order of effective nuclear charge. This is the order, and it is also the order of stability, because stability is directly related to effective nuclear charge. Greater the effective nuclear charge, greater is the stability. So this order is the order of stability also. Now stability and energy, these two are inversely related. When stability high means energy low, stability less means energy high. Inverse relationship. So that is why now when you consider the energy of the orbital within same principal quantum number, then this should be the order of energy. F is higher energy than D, D is higher than P, P is higher than S. Okay. So we'll end here. Thank you for listening.